In this last video of the chapter, we'll look at some examples of and applications of the Jacobi criterion that we have seen. And the first one is, in fact, somehow an application of this criterion followed by an application of the blowups that we have seen in the last chapter. So let's start with our nice curve, the vanishing set of x squared, x2 squared minus x1 to the 3, this kind of customary curve inside A2, sorry, A2 of over the complex numbers for simplicity. Let's call this equation here F. Then the Jacobi matrix J is just given by these partial derivatives. And well, we can do those. You get minus 3x1 squared and 2x2. And we can easily calculate the rank of this. Well, if you plug in the point 0, 0, then you see both components vanish, and so the rank is 0. At all other points, if you don't plug in 0, 0, since we're in characteristic 0, then you see that you always get a non-zero vector, and so you get rank 1. And then in the Jacobi criterion, we had this n minus the codimension, but x3 is irreducible of dimension 1. So this codimension is always 1. And then we have 2 minus 1 is equal to 1. And so the criterion says that x3 is smooth at all points p, except at p equals 0, 0. And this reflects our intuition that this is the one point where something goes wrong. And then, in fact, what we can do is we can take this blow up of this singular point inside x3 and see what does this local operation do. We have seen that blowing up this thing at this point is the same thing as blowing up the entire space A2, and we get this A2 tilde, and then taking the strict transform. And so here, let's see what this actually looks like. What is the strict transform? Let's see it in concrete equations. The claim that we have here, at least from the picture, is that the exceptional locus of this blowup is exactly a single point inside x3 tilde here. So let's try to check that. And so we know that the coordinates on A2 tilde, the blowup, which sits inside A2 cross P1, you have the two original coordinates from A2, and then you have these projective coordinates y1, y2, and the equation that they satisfy is that x1, y2 is equal to x2, y1. And so to do a concrete calculation, let's look at a particular chart here. And let's look at a chart where y1 is non-zero. That's one of the two patches of this P1 coordinate. Let's look at this chart, and then this thing is just isomorphic to A2 with coordinates x1 and y2. Because, I mean, somehow being in the chart y1 non-zero, in P1, this means you can just set y1 to be 1 and then have one more coordinate y2. So y1 is equal to 1. And then this equation here, so y1 being 1, then just tells you that x2 is equal to x1 times y2. Okay, so we have on this chart A2, we can express all of these coordinates just uniquely in terms of these two coordinates. And then let's see what happens with the equation. So somehow we want to take the pre-image now of x3 under this projection. So x3 was cut out by this x2 squared minus x1 to the 3. And so x1 is one of the coordinates. We leave it intact. And x2 we have seen is given by this equation here. So let's plug in x2 is equal to x1 times y2. Yeah. So we just did this substitution here. And then you see now we have an equation. This sits inside this A2 with these coordinates. And where we see we can factor this equation. So this is x1 squared, y2 squared, minus x1 to the 3. And this factors as an x1 squared we can draw out. And the remaining thing is an x2 squared minus, and there's one factor left, x1. So minus this. And you see somehow this x1 squared, this is in fact, so somehow x1 is equal to 0, and then x2 is also equal to 0. And y2 can be arbitrary. So somehow this would be this entire p1, the entire exceptional divisor of this a2 squared. So that we're not interested in. This is not part of the strict transform. But the other part is much more interesting. This y2 squared minus x1. This is then exactly the x3 tilde, or at least the x3 tilde intersected with this chart. And so we can describe this here explicitly. And you see somehow in the picture, this curve also looks like one of these parabolas. So basically one coordinate is the square of the other coordinate. And then the critical point here, when x1 and x2 are 0, this then forces y2 to be 0. And y1 is always 1 in this chart. So this is exactly this point A. And we see, I mean, somehow in local coordinates here, this thing just looked like the standard parabola. We have seen the standard parabola is smooth at the origin. And so the x3 tilde is smooth at this point. Why is this interesting? Well, it's interesting because we started with this curve x3, which had a singularity at this point. And then after blowing it up, the singularity, the blow up x3 tilde is actually smooth at all the preimage points, or at the unique preimage point. And something like this is called a resolution of singularities. And so somehow the idea is when you have a singular space and you blow up some of its singularities, then this tends to make them nicer. And I don't want to go into details what it means to tend to be nicer, but somehow that's a general strategy if you want to start with something singular and obtain something smooth. And to look a little bit beyond the scope of the lecture, in fact, there is a conjecture in algebraic geometry which is still open, which is called the conjecture on resolution of singularities. And let me formulate one version here where we have all the words needed. Namely, let's say we start with x being a proper and irreducible variety, or in other words, x is a complete, so you could also replace this by complete and irreducible variety. Then the claim is that there exists a smooth and complete variety x prime together with a birational map from x prime to x. So in other words, you start with something complete and irreducible. It might be singular, but then there exists a smooth complete variety together with a birational map. So you can replace this singular object after a birational transformation. You can replace it with a nice smooth thing. And this conjecture was proven by Hironaka if the characteristic of k is equal to 0. And for arbitrary k, you can also prove it in dimension if the dimension of x is at most 3, but the general case is still open. So this is one of the big open problems in algebraic geometry. And I just wanted to mention it here. And I mean, certainly blowing up singularities is one way in which you can try to find such an x prime. And you see, I mean, in this very special case that we had above, we did succeed, because somehow we started with something singular and then we found a smooth thing which maps birationally, because we know that away from the center of the blow up is actually a birational map. Okay, so this was one application. The other is some nice property of the locus of all smooth points in a variety, because in fact it turns out that being smooth is an open condition, in the sense that if you let x smooth inside x be the set of all smooth points, then this turns out to be an open set. And so let's expand the proof here. So let's say you have a nx smooth point. Then we want to show that it has an open neighborhood of smooth points. So we want to show A as an open neighborhood of smooth points. And we want to get into a range where we can apply the Jacobi criteria that we like. And so the first statement is that where we go to this affine Jacobi criterion. So in other words, restrict after restricting to an affine open containing A. So without loss of generality, we can assume that X sits inside some AN as an affine variety. And the other thing that we have seen, so now the next thing is in the Jacobi criterion, we have this kind of straight codimension of X at the point A. And we want to make our life a bit easier. And the good thing is that we have seen, because in general, when X is a reducible space, this codimension might be a bit complicated. But we know that if A is a smooth point, this implies that this ring OXA is a regular local ring. We had this connection to commutative algebra. And then we saw from it that X is locally irreducible at A. So this means there's a single irreducible component of X containing A. And so we can just restrict to by taking the complement of all of the other sets xj, which are the irreducible components of X, which don't contain A. After we throw all of them out, we are then left with an irreducible space. And then we can maybe even shrink again to an open affine neighborhood. And so we have then restricted to the, or we have reduced to the case so we restrict first of all to an irreducible affine neighborhood of A, and then the final setting in which we actually tackle this conjecture or this proof now is that is X inside AN is an irreducible subvariety, and A is a smooth point in there. And then the good thing is that this codimension of any point P here is just given by the dimension of X for all P in X. And that's nice because then in the Jacobi criterion, one side is always the same number. And now the Jacobi criterion tells us that the locus of smooth points, these are exactly the points P inside X, such that the rank of JP, where JP, this is the Jacobian matrix at P, for some set of generators of the ideal of X, this should be greater or equal this n minus dimension of X. This is the right-hand side. And then So we have reduced this definition here to purely equality or inequality of this rank of this matrix, but the claim now is having rank at least some fixed number. This is some open condition. On X, because, I mean, having rank at least some number just means that one of the n minus dim x cross n minus dim x minors of this matrix JP does not vanish. So in other words, this X smooth inside X is the complement of the locus where all of these minors vanish. So it's the complement of a closed, theoretically closed subset. And so it is open. And this finishes the proof. Okay. And so, so we see the set of smooth points is open. And in fact, something stronger is true. This is called the generic smoothness. And this says that not only is this an open subset, but it's actually always a dense subset. So it can, for example, never be the empty set if X is non-empty. And when X is irreducible, this is in fact enough to be non-empty. So we can always find at least a smooth point. And this is not super easy to show. And a reference that Gartman gives is this book, Hard-Drawn Algebraic Geometry. It's some theorem here, which you can look up if you're interested. We don't really need this, but it's a good thing to keep in mind that being smooth is not a very crazy condition because kind of away from an open and or somehow away from a closed set, which cannot be everything, you are always a smooth point. And so we are not going to prove it in this generality, but at least let's say for a particular setting, let's see how to prove this. And the setting is the setting of a hypersurface. X is equals to the vanishing locus of f inside an, where f is some polynomial, which let's say it's non-constant and it's irreducible. Let's look at an irreducible hypersurface in an. And then we show that the locus of smooth points is non-empty because X is then also irreducible. This is then automatically a dense subset. Any non-empty open subset of X is dense. And so assume otherwise. So let's say this here was the empty set. That means that the Jacobian matrix would have rank, and you can check, would have to have rank 0 at all of the points. In other words, all of these partial derivatives here would have to vanish at all points a and x. And this of course means that these polynomials here, they vanish at all points of x. So in other words, they're contained in the ideal of x. But by the Nullstellensatz, the ideal of x is just given by this one equation cutting it out because f is irreducible. And so here we're already seeing this is a bit strange because we have a single polynomial, but then all of its partial derivatives should be multiples of this polynomial. And this is a bit strange, right? Because the degree in, let's say, the variable xi of this partial derivative is strictly smaller than the degree of xi in this function f itself. And so this can only happen if, in fact, taking this derivative got you the 0 function. That's the only function whose degree can possibly be smaller than this one here. Or sorry, I mean somehow what you want is that this here must be a multiple of f, and so somehow the degree must be at least f, unless it is actually a 0 function. Okay, so we have reduced. This can only happen. This thing being empty can only happen if all of these partial derivatives are 0. And now we have to distinguish two cases. If the characteristic is 0, then having all of these partial derivatives vanish means f has degree at most, or I guess sorry, this should be strictly less than 1 in all of the xi. Because I mean it cannot have any linear term, quadratic term, and so on. And so it must actually be constant. Yeah? But we assumed it's non-constant. So that's the contradiction. In characteristic P, something annoying can happen. Namely, I claim that in characteristic P, such a polynomial has vanishing partial derivatives in all functions, in all of the variables xi, if and only if it is a polynomial in the P's power of the variables. Because I mean, you see in characteristic P, for example, if you take the derivative of x1 to the P by x1, and you get P times x1 to the P minus 1, but P, the constant, is 0 in characteristic P, so actually you get 0. But this is a function, even though its partial derivatives all vanish, it's still not a constant function. But I mean, just writing down f as a sum of monomials and checking these conditions, you can see this can only happen if you're a polynomial in these P's powers. So f is of the form g of x1 to the P up to xn to the P. And then in characteristic P, something very nice happened, and this is called often the freshman stream. So the original freshman stream is this here, this equality here in fp of x1, x2, namely that if you have a sum of two things and you take it to the P's power in characteristic P, then actually this P's power just draws in. Like normally, this here would be a very bad calculation mistake, right? Just drawing in a P's power. But in characteristic P, this freshman stream is actually satisfied and you can do it. The reason is in the formula for the binomial, if you expand this here, all of the binomial coefficients for all except for these extremal powers contain some factor of P. And so all of them vanish inside this unit fp. And so here you see for this polynomial g of x1, x2 equals x1 plus x2, it's true that if you take it to the P's power, it's the same as taking the polynomial and plugging in x1 to the P and x2 to the P. And this holds true more generally. So somehow if you have this polynomial, you take it to the P's power, then the P's power draws into each of the arguments. So that's kind of basically the very similar argument to the one here also shows this. So you can kind of draw out this, but then now we reach another contradiction because we had started all the way up here. It started with f being an irreducible polynomial, but now we have written it as the P's power of another polynomial. This cannot happen. And so finally we did reach a contradiction to this assumption that x smooth is empty. Okay. So this was kind of expanding out, at least in this small example of a hypersurface, that the locus of smooth points is non-zero. And we did have to distinguish some characteristic. And so the final thing in this chapter is a concrete example of such a smooth hypersurface. And in fact, a smooth hypersurface inside projective space. And these are the so-called Fermat hypersurfaces, and they will be relevant in the next chapter. So you fix some positive numbers n and d, and then inside the projective space Pn, you can look at this vanishing locus of this homogeneous polynomial, which is just the sum of the d's powers of all of the variables. And this thing is called the Fermat hypersurface of degree n, of degree d inside Pn. And the claim is this is a smooth hypersurface. It's actually smooth at all points. And so for this, well, we calculate, we had, if you recall, there was a variant of the Jacobi criterion, which was the projective Jacobi criterion. And so for this, we just took this, this vector of partial derivatives. So this always gives d times xi to the d minus 1. And the Jacobi criterion says that if this has rank equal to 1, then this thing is smooth of codimension 1. Okay, and again, we have two cases to distinguish. If the characteristic of K does not divide D, then we can kind of throw out all of these vectors here. And then we see this vector here is 0 if and only if the xi to the power d minus 1 are 0. But all of the xi to this power d minus 1 being 0 is only possible if all of the xi themselves are 0. But this is not an allowed point inside the projective space Pn. Right? We don't allow the 0, 0, 0, 0 vector. And so this can actually never be 0. So its rank is always 1 at all points. And then the projective Jacobi criterion tells us, okay, it's smooth of codimension 1. And then in this final annoying case, let's say P, the characteristic of K, divides D, which means, well, you can draw out factors of P until the remainder no longer is divisible by P. So you can split D as some D prime times some power of P, where P does no longer divide any factor in D prime. And then, well, now comes the freshman stream again, because X is this vanishing set here, right? But now D is equal to D prime times P to the R. And then the same freshman stream allows us to pull out this P to the R, because we're in characteristic P, and get this remaining term. But then the vanishing locus of this here, this is 0 if and only if each of the factors here is 0. So in other words, if this thing is 0. So we have actually reduced, in this case, the Fermat hypersurface of degree D. We have just seen it's the same thing as the Fermat hypersurface of degree D prime. But now we're in good shape, because now, by assumption, the characteristic no longer divides the D prime. And we have already checked this case and have seen it's smooth there. And so we have kind of reduced, after pulling out this extra power, we have reduced to the case that we already checked. And so this finishes the proof. And so we see this Fermat hypersurface is indeed smooth. So this is everything about smooth varieties and the tangent spaces. And so now in the next chapter, we are going to combine all of the different notions that we have seen so far and talk about the set of lines on a smooth cubic surface.